Alright guys, so we're going to start the last video of the week, which is dealing with solving force problems and some force practice problems. So here is just a slide that has some common equations over here on the right for like force of gravity, friction, force friction, net force, the components, finding components with cosine and sine in the x and y directions, and then just the general premise of what you need to do to solve force problems. So the first thing you're going to do is always draw a free body diagram. Then you're going to fill in the table with our positive, negatives, and zeros to indicate directions. Then we're going to use our equations to solve for the forces. So if you need to use any of those to get a number, do that. If something's at an angle, you got to use the cosine and sine and got to do some trig. Then we're going to add the vertical columns, so the forces in the x and the forces in the y, to get the net force x, net force in the y, and that'll get you probably a net force is equal to ma kind of equation set up and solve for a. So we're going to do this in a couple things, and I've already tried to get this set up. Let me flip that. That's what I'm trying to do. Left, right. Yeah, okay. So in the first problem, it says a 4 kilogram box is sitting on a table. The box is being pushed and has a net acceleration of 4 meters per second squared to the right. There's a friction force of 12 newtons. We're going to draw the picture, our free body diagram of the situation, and fill in our chart with our x and y's. And again, this is a little bit older, so you might not have the exact same notation, but it would be like Fg, Fn, force of push, net force, and we want to figure out what the coefficient of friction is between the box and the table. So we're going to do all that work here on this first problem. So I've already set up the free body diagram. So I drew and labeled the forces. So I drew a gravity force going down. So if this dot here represents where all the forces act on the box, we had a gravity force going down. We have a normal force going up, we have a pushing force going to the right, and we have a friction force going to the left. So if you think about just a box sitting on the table, those up and down forces or vertical forces are going to be balanced, so they're going to kind of cancel out, and we have our normal force and gravity doing that. The box is accelerating to the right, so the pushing force going to the right is larger than the friction force going to the left. So remember, so that's basically our free body diagram, and the arrow right is bigger than the arrow left. That's really the only one that probably you could have messed up. But we're going to go through and list out these forces, so let me do that. So we have a pushing force, so I'm going to just say F push. So again, you just get these labels in this chart over here from your pictures. So we have the pushing force, we have the force of gravity, so that's Fg. We got our normal force Fn, we got our friction force Ff. And this is moving, so it would be technically FFK. If you just wrote FF, that's okay. It's kinetic friction because it's moving. And then we have our net force, which is the bottom box here out of our chart. I'm going to switch up and use a smaller calligraphy pen, and that'll work better. So we did step one. We drew our free body diagram. The next thing we need to do is fill in our chart with our positive, negatives, and zeros. So coming back here, positive, negative, and zeros, I'm just going to do plus minus 0 for all of these boxes. So the pushing force is going to the right in the x direction, so that's positive because x direction is left to right, and the y direction is the vertical part, that's the up or down. So again, up is positive and down is negative, right is positive and left is negative. So push is going to the right here, so that's a positive force. It is not going up or down, so it's going to be 0 in the y. For the gravity force, and this is supposed to be Fg, so I'll make that a G, make it look more like a G. Gravity is trying to pull down, so it's 0 in the x, it doesn't go left or right, it just goes down, so that's negative there. Normal force is only going up, so it's 0 in the x and positive in the y. And the friction force is going to the left, so it's negative in the x, and it's not going left or right, so it's 0 in the y. We talked about these up and down forces balancing out, because if they didn't balance out, then it would be thrown off the surface or fall through the surface, so that is also going to be 0 in that bottom box. And we would expect that the net force is going to the right, so this would probably be positive, and the numbers should show us that. Okay, so so we have all these different forces now, and we've labeled their directions, and now we got to figure out the actual values that go in these boxes. Alright, so we need to just fill in these numbers here, and the pushing force is one of the things that we're actually looking for, so I'm going to leave that blank. Gravity we can calculate using an equation, so Fg for the force of gravity is equal to the mass of the object times the acceleration due to gravity. So the mass is 4, so I'm going to put a 4 in for m, for 4 kilograms, and then 9.8 is the acceleration due to gravity. So 4 times 9.8 gets you 39.2. So I'm going to write 39.2 in the box for this gravity here in this box, so negative 39.2. It's negative because gravity is trying to pull down. If you look at that column, we have actually everything we need for that column except for the normal force. So we're looking for the normal force. So if this is 39.2 going down for the force of gravity, then the normal force to keep it from falling downward is going to be a positive 39.2. It can't be bigger or smaller than this in this case because there aren't any other forces acting up or down. So these are balanced. So we had a negative 39.2 newtons for gravity. We got a positive 39.2 newtons for the normal force. So we have those two. We got B and C. The pushing force, the net force, and the other stuff. Friction, it told us the force, so that was 12, so I can just write that in. Sometimes they will make you calculate that. So we're looking for these two things. The pushing force, there's no formula for, so we're going to have to like figure that out using the chart. So I'm putting that blue box like I did down here for the normal force. That didn't have an equation. The net force we can actually figure out. So the net force, the overall force acting on it, on this object is the mass times the acceleration. That's Newton's second law. So if we know the mass again, which is 4, and the acceleration, which in the problem it says it accelerates at 4 meters per second to the right. So that's a 4. So 4 times 4 is just 16. And it's a positive 16 because it's going to the right. So some number minus 12 gets me 16. So we just got to figure that out. So if you put in 28 here for the pushing force, so 28 minus 12 will leave you 16. So that is my my pushing force too. So I got my pushing force, I got my net force. I've done everything except for what is the coefficient of friction between the box and the table. So the coefficient of friction, that's the Greek symbol U, or mu, mu. It looks like a cursive U, the way that I read it. And we're going to use the friction force for that. And we have everything that we need. So the force of friction is equal to mu times Fn, or I call this the fun equation because it's F and a U and an N. It's probably not that fun for you. But anyway, the friction force is 12. You don't have to worry about the positive or negative. The coefficient is always a positive value. So if you put a negative here and you made it a negative, I would still give you credit, but just, you know, you can just leave it out. And then 39.2 is the normal force that we found. So now that we have both those things in, we can solve. We're going to solve through division. So you're going to take and solve for U, and that would be 12 over 39.2. And let me just put that in the calculator quick because I forgot to calculate that one. So 12 divided by 39.2 is 0.306. So this U value is always a decimal. It's always less than 1. So 0.306 is fine. If you just said 0.3, that would be fine, or 0.31, that's okay as well. So that is the first of these problems. Okay, so we're on to problem number 2 out of 3. So this one says a box that weighs 196 newtons is sliding along the floor. There's a rope pulling the box at 160 newtons at an angle of 60 degrees above the positive x direction. And then the coefficient of friction between the box and the floor is 0.174. We're going to do the same kind of things that we did in the last problem. We're going to draw a free body diagram. We're solving for the mass of this object. That was new, but we can do it. It's not a problem. The force of friction, the normal force there, Fn, the force of friction, Ff, and then the net force, and then eventually this acceleration. So there's a couple more things we're looking for, but it's really the same kind of work. I already drew the free body diagram here. I'm just going to label the different things. So the force pulling down, that should be the force of gravity. So I'm going to have you guys answer some of these. This force I have going up and to the right based on this description is the force pulled on the rope. So I'm going to label that the tension, so Ft. The force from the surface, that's the normal force. And the box is eventually going to slide to the right, so the friction force would be going to the left, and that's going to be kinetic friction. If you wanted to write a little k here, you could. If you just write Ff, that's okay, because we only have one type of friction in this problem. So those are the 4 forces. We're going to fill in our table here. So with gravity, Fg, the tension force, which I'm going to label Ft, the normal force, Fn, the friction force, Ff, and eventually we are going to solve for the net force, which is F net. Okay. So those are the forces, and we need to label which directions they are headed. So let's look at these individual forces, and the arrows show you the direction, so we just have to indicate that mathematically with positives, negatives, or zero. So if we look at gravity first, because that's the first one I have listed, gravity is going in the negative y direction. It's going down, so that's a negative, and it's not going in the x, so that's a 0. If we look at this tension force, this pulling force, it's going to the right, it looks like. So I have a little blue arrow going to the right there. I have a little arrow going up, so that's going up and to the right. So it's positive in the x because right is positive, and it's positive in the y because up is also positive. So I have a positive, positive there. The normal force is only going up, so it's not going in the x, so that's a 0, and it's positive in the y. Friction is going to the left, so that is negative in the x, and it's not going up or down, so that's 0 in the y. And again, this box is going to slide along the floor. So if it's sliding along the floor, it's not accelerating up or down, so the net force up and down is 0. So all these forces that we add up, the gravity in the y direction, the gravity which is down, the tension which is up, and the normal force which is up, they're going to all cancel out and get me to 0. It'll be balanced. In the picture here, the box is going to slide to the right, so I would expect this to be a positive value for the net force and the x. So we filled in all our positives, negatives, and zeros. That's good. Now we just have to take and try to solve for some numbers if they don't give us anything. The box, it says weighs 196 newtons, so that's a weight. It's in newtons, so that's a force. Weight is the same as the force of gravity, so we're going to put in 196 for this box right there and be done with that. We're actually asked to solve for m, so we're going to use the gravity equation. We used the gravity equation last problem. We had the mass and we were looking for the force of gravity. This time we're looking for m. It's also going to be useful because we need it at the end of the problem when we solve for the acceleration. So we're going to have 196 here for the force of gravity. The mass is what we're looking for, and 9.8 is g. So when we divide through by 9.8, you're going to get 20 for this answer for m. So when you divide through, you get m equals to 20. That's going to be useful later on. I don't really need it right now. This second, I could do other stuff. 20 kilograms, because mass is measured in kilograms in physics. In chemistry, it was probably just grams. But we're going to use that piece of information later on when we get to the end of this problem. So the other ideas that we have, the tension, we can work with that because it says 160 newtons at 60 degrees above the positive x. The part that's a little bit difficult here is that it is going at an angle, so we have theta. So we know the angle is 60 degrees, we know this is 160 newtons, and we have to actually solve for the force of the tension in the x and the force of the tension in the y. So those are those components that we've talked about in other vector videos to help you remember how to do that. So, so we're going to plug in the numbers in the chart. I usually just write it out here. So this would be like 160. So 160 cosine of the angle, which is 60 degrees. Now, you would put that in your calculator and solve it. I've already done that. That turns out to be 80 because cosine of 60 is a half, and half of 60 would be 80. So it's a positive 80 because it was going to the right. We're going to do similar work for the y component of the tension. So that would be 160 times the sine of the angle, which is 60 degrees. This one doesn't round as nicely. It doesn't turn out to be a whole number. It turns out to be 138, and I'm just going to round it to 138.6. Okay. So we're through, I think, what we can do. We could try to solve for the force of friction, but we're going to have trouble with that because the force of friction equation is FF equals mu times n, or Fn, the normal force. So we actually know the mu value, which is the 0.14. They told us that in the problem, for 174, excuse me, I'm speaking too quickly. But we don't know Fn yet. So we have to get Fn first. So we got to fill in this box here that I just put for the normal force before we can plug in here and take that value and put it in here and then solve for the force of friction. So it's going to be a kind of process to work through this, but that's okay. So for this column, if we add these together, we have 196 in the negative direction, and we have 138.6 in the positive direction. So that's kind of how much this pulls up for the tension and how much gravity is pulling down in the y, and the normal force makes up the difference. So we're going to go ahead and do that math. And if we do, this value for the normal force is 57.4. So just pointing this out again and reinforcing it, the normal force is not always equal to the gravity. Like a lot of times, because there are only two forces up and down, they do cancel out and they're balanced, but they are not the only force here in this situation because we're pulling up on the rope. So we're taking away some of that gravity force and the normal force doesn't have to push as hard. So now we have this number, we can put it in here. So that's 57, if I could write 57 in there, 0.4. And then we will multiply that by 0.174, and let me type that in the calculator because I did not. So 0.174 times 57.4 gets you 9.9876. I'm just going to round that to 10 just to make it easy. So that's 10. We're just going to say it's 10. So that's going to go in for our friction. So again, after we found our normal force, we can use the coefficient times that number and get the friction force. Now it's just adding again. So 80 plus negative 10, because these are both zeros, 80 plus negative 10 gets you a positive 70. And we are almost done. If you look back and check everything that we've done, we've solved for our mass already. We found the normal force, we solved the friction force, we found the net force, and now it's getting the acceleration. So we're going to use F equals ma, or net force is equal to ma. Again, I tried to provide these equations at the beginning, so you can use them at the beginning of this slide, or have them as a link in D2L that you can pull up and print out if you want. So we have 70 equals 20 times a, and we're going to solve for a, so a is equal to 70 divided by 20, and that's going to get you 3.5. Let me just double check that, but 70 divided by 20 is 3.5, so I can trust my math, but I always check the calculator anyway. Use the calculator. As long as you type it in right, it'll get you the right answer. So 3.5, that's going to be meters per second squared. And that's going to move to the right. So that is in the positive x direction. That's what that positive indicates there. And this is the positive direction. So that's the answer for your last part there, which is the net acceleration. We have one more to go through, so let's go ahead and try to start working on this one. So this one says a 3 kilogram book is shoved with a force of 12 newtons at an angle of 22 degrees below the positive x direction. The coefficient of kinetic friction between the block and the surface is 0.08. And again, we're going to solve for the free body. We're going to set up our free body diagram. We're going to figure out the rest of our chart, figuring out the positives and negatives and zeros, all the values for all the different things, and then we're going to solve for the net acceleration at the end. Okay, so let's go ahead and start labeling this free body diagram. I already drew the pictures, but what force would be going down? That's the gravity force. So that's Fg. This arrow is slightly below the horizontal, so if I draw that dotted line in, this is going to be the pushing force or the shove. I'll just write F push. That seems to work okay for most people to understand what I mean. So we're pushing down and to the right, and that's true because it says it's at an angle of 22 degrees below the positive x. So below is down and right is positive x. So it's down to the right. Because we're pushing down, there's a component in the pushing force that is kind of trying to go down. There's also a component trying to go to the right. That's why the push is going down and to the right, like it's labeled there in black, like that. So so we have two components. So we have the red arrow going down and this gravity arrow going down. So the normal force arrow, if I kind of trace it here in green, that's going to be the normal force, and it's going to have to be bigger than the gravity force because we're adding an extra amount of force pushing down. Okay, and then finally the last arrow here going to the left would be the force of friction, which is going to try to oppose the motion, but it's probably going to slide, so that makes sense. So let's go ahead and write in these values here. So we have our gravity force, Fg. We have our normal force, or our pushing force. I'll say that next. So push, F push. There you go. The normal force and the friction. And when you add all those together in both directions, you will get the net force. And again, most of the time with this net force, if we're only moving in or accelerating in one direction, That's a better way to say it. If the net force is only in one direction, that means it only accelerates in one direction, and you get a 0 for a lot of times for this y, and that's going to happen again in this case as well. So let's go through and do the plus minus zeros. We already put a 0 there. According to this, it looks like it's going to slide to the right, so I'm going to put a plus sign there. If you don't get that, then maybe that's not what the case is, but mathematically that should work out for what's happening here. Gravity is not going in the x direction, so it's 0. It's pulling down, so it's negative in the y. The pushing force goes right and down, so right is positive, and y direction down is negative. And then the normal force is not going in the x, so that's 0. It's going up in the y, so that's positive. Friction force is directed to the left in my picture there, and it is not going in the y, so that is 0. So those are those charts for our different values for the different forces. And let's go ahead and try to figure these out. 3 kilograms, that's a mass. So we can do the force of gravity, Fg here, is equal to mg. So I'll write this equation right next to Fg on the chart, or on the free body diagram. So it'll be 3 times 9.8. It's going to be close to 30. It's 29.4, I believe. Yes. So 29.4 is the amount of force that is acting. 29.4 newtons is the amount of force that is trying to pull down, downward. For the pushing force, we're going to do similar work to what we did last time with the cosine and sine bit. So the force is 12 newtons, and it's going at 22 degrees. So it's 12 cosine of 22. And then for the y, it would be 12 sine of 22. So again, I'm going to put those in my calculator here. You should try that at home to make sure you get the same values that I do. If you don't get the same values, then I would suggest your calculator is either in the wrong mode, or you're entering things in the wrong order specific for your calculator. I write it the way that it looks on my calculator, so that's the way I'm doing it here, and for most calculators it works that way. But if you're using like an Apple phone to try to do this math, that's not great. But you should probably turn it around, and you have to do it backwards. So it would be 22, then hit the cosine button, and then times 12. So I get 11.13 for that one. And when I did 12 sine of 22, I got negative. It's negative because I have the negative there, 4.5, because it's pushing down. Okay. So again, we're sort of at the same place that we were last time, where we have all the boxes in the y direction except for the normal force, and that is what you're going to always have to do to find the normal force, because the normal force does not have its own equation. So I have negative 29.4 and a negative 4.5, and they're both going down. So to cancel that out, we would need 33.9 newtons to go up and make it go to 0. So this upward force and these two downward forces here are all balancing out. Then we have our normal force, so then we can use our friction equation. So the friction equation is Ff, force of friction, is equal to the coefficient times the normal force. So mu times Fn, or that cursive u there, times Fn. So that's going to be the coefficient, which is 0.08. So 0.08, and then we're going to multiply it by the 33.9. So when you do that, and you put that in your calculator, and it will shoot out a value of 2.71. So I'll write 2.71 here, just so I'm consistent with what I did on the other page that you're going to have access to in D2L that has all this worked out. And then it's just addition, 11.13 plus a negative 2.71, and that's going to get you 8.42. So 8.42 is the net force. That is the overall amount of force, and we're going to use the net force equation where Newton's second law says the net force is equal to ma, and solve for a. So we have 8.42 equals the mass, which was 3, times a. We're going to divide through both sides by 3 and get an acceleration equal to, let me erase and try to write this out better because it's really small there. So I would have a is equal to 8.42 going to the right divided by 3. So I just did it here, and then it worked out that it's like with that number in the chart. And when you do that, you should get a value of 8.42 divided by 3 of 2.806, but I'm just going to say it's 2.81. That would be meters per second squared because it's an acceleration, or meters per second, and it is directed in the positive x direction, so that is to the right. So that is your answer for A here at the very end of this third problem. Okay, so I'm going to stop there. That's about 25 minutes, so that's plenty of time. Hopefully that was helpful and helps you kind of look at some force problems and be able to work through them. So have a great day.